Hello everyone, my name is Matan here from Civil Engineering Department of Paragon International University, and today video is about my term project of M132 Calculus 2. And the topic is about Chapter 10, Infinite Sequence and Series. 10.10, the binomial series and applications of Taylor series. So I'm going to show how the Taylor series are used in applications, and I will also introduce the binomial series of the binomial expression, which is 1 plus x to the power of m. And here are the contents of my video. I have 5 points. So the first one, the binomial series for power and roots. The Taylor series of the function fx equals to 1 plus x to the power of m, when m is constant, is 1 plus mx plus m times m minus 1 over 2 factorial times x squared plus m times m minus 1 times m minus 2 over 3 factorial times x to the power 3 plus until m times m minus 1 times m minus 2 times m minus 3 times until m minus k plus 1 over k factorial times x to the power k plus so on. And this series is called the binomial series. It converts absolutely for absolute value of x equal to 1. And if you want to know how did they get this binomial series, so first list the function and its derivative. So here we have the list from fx until k derivative of fx. And then we have to evaluating all of this at x equal to 0. And then we have to substitute them into the Taylor series formula. So we will obtain this binomial series. And if m is an integer greater than or equal to 0, then the series stops after m plus 1 terms because the coefficient from k equal to m plus 1 on is 0. And if m is not a positive integer or 0, the series is infinite and converts for absolute value of x equal to 1. And here is the binomial series formula for x greater than minus 1 less than 1. So 1 plus x to the power of m equal to 1 plus the sum of m choose k times x to the power of k from k equal to 1 to infinite, where we define m choose 1 equal to m, and m choose 2 equal to m times m minus 1 over 2 factorial, and m choose k equal to m times m minus 1 times m minus 2 times m minus 3 times until m minus k plus 1 over k factorial for k greater than or equal to 3. And here is the example. If m equals to minus 1, so the solution minus 1 choose 1 equal to minus 1, minus 1 choose 2 equal to 1, and minus 1 choose k equal to minus 1 to the power of k. Then you get the answer. 1 plus x to the power of minus 1 equals to 1 plus the sum of minus 1 to the power of k times x to the power of k from k equal to 1 to infinite equal to 1 minus x plus x squared minus x to the power 3 plus until minus 1 to the power of k times x to the power of k plus so on. And here, sometimes we can use the binomial series to find the sum of a given power series in terms of a known function. For example, they give us this power series, x squared minus x to the power 6 over 3 factorial plus x to the power 10 over 5 factorial minus x to the power 14 over 7 factorial plus so on, equal to here sin x squared, because sin x equal to x minus x to the power 3 over 3 factorial plus x to the power 5 over 5 factorial minus x to the power 7 over 7 factorial plus so on. Because here you can see the series of sin x, but they substitute x squared into the series. So here you can get the answer sin x squared. And the second point, non-elementary integrals. They said that Taylor series can be used to express non-elementary integrals in terms of series integrals, like integral sin x squared arise in the study of the diffraction of light. So example, they want us to express integral sin x squared as a series. So the solution, they have to express sin x squared as a series first. So here you know about the series of sin x squared. Then we have to integrate it. Then here the answer, we get the series of integral sin x squared. So the third point, arctangent. The series of arctangent x equal to x minus x to the power 3 over 3 plus x to the power 5 over 5 minus x to the power 7 over 7 plus so on. When we differentiate and then integrate arctangent x, So we get the series of arctangent x. But they said that the series didn't prove the term-by-term integration theorem. On the conclusion, it depended. So here is the proof. Derive the series by integrating. So we had to integrate arctangent of t. Then we get this equation. And the last term comes from adding the remaining terms as a geometric series with first term a equal to -1 to the power of n plus 1 times t to the power 2n plus 2. And the ratio a equal to -t squared. Then integrating both sides of equation 2 here, equation 2, from t equal to 0 to t equal to x, it gives the series of arctangent x equal to x minus x to the power 3 over 3 plus x to the power 5 over 5 minus x to the power 7 over 7 plus until -1 to the power of n times x to the power 2n plus 1 over 2n plus 1 plus an of x, where an of x equal to integral from 0 to x of -1 to the power of n plus 1 times t to the power 2n plus 2 over 1 plus t squared. And the denominator of the integrand is greater than or equal to 1, then the absolute value of an of x less than or equal to integral from 0 to absolute value of x of t to the power 2n plus 2 equal to absolute value of x to the power 2n plus 3 over 2n plus 3. And if absolute value of x less than or equal to 1, then the limit n approaches infinite of an of x equal to 0. And here is the sum and the series of arctangent x. Arctangent x equal to the sum of -1 to the power of n times x to the power 2n plus 1 over 2n plus 1 from n equal to 0 to infinite for absolute value of x less than or equal to 1. And the series of arctangent x here you can see. And when we put x equal to 1 into the equation above, we have to put x equal to 1 into the series of arctangent x. Then we get the Leibniz formula here, the Leibniz formula. And the Leibniz series converges slowly, so it's not used in approximating pi because it gives many decimal places. Instead, many people use the series of arctangent x to compute infrared trigonometric identities, since it converges most rapidly when x is near 0. For example, alpha equal to arctangent of 1 over 2 and beta equal to arctangent of 1 over 3. And the solution, tangent alpha plus beta equal to tangent alpha plus tangent beta over 1 minus tangent alpha tangent beta equal to 1, and 1 equal to tangent pi over 4. And also pi over 4 equal to alpha plus beta equal to arctangent 1 over 2 plus arctangent 1 over 3. And then we can substitute x equal to 1 over 2 and x equal to 1 over 3 into the equation number 3 in the last line to get the value of arctangent 1 over 2 and arctangent 1 over 3. And then we multiply the sum of this result with 4 and it will give us pi. So the fourth point, the indeterminate forms limit. We can actually evaluate the intermediate forms of limit by expressing the functions as Taylor series. For example, we have to evaluate limit x approach 1 of ln x over x minus 1. So the answer, first we have to express ln x as a series. Then we evaluate the limit. So the answer is 1. And another example, they want us to find the limit x approach 0 of 1 over sin x minus 1 over x. And here, the solution, we have to express the function as a series first, and then we can evaluate the limit. So the answer is 0. And I also want to add something, the approximation formula for cosecant x. As you may know that many people use this example to find the approximation formula for cosecant x. Here, as 1 over sin x minus 1 over x approximating to x times 1 over 3 factorial approximating to x over 6, then cosecant x equal to 1 over x plus x over 6. And here is the last point, Euler's identity. The definition of Euler identity for any real number theta, to the power e theta equal to cos theta plus e sin theta. And if you want to know how did they get this equation, so first substitute x equal to e theta when theta is a real number into the series of e to the power of x. And here you can see that we substitute x equal to e theta into the series of e to the power of x, and then we get cos theta plus e sin theta. And also this equation let us define e to the power a plus be to be e to the power of a times e to the power of be for any complex number a plus be. And one consequence of the identity is the equation e to the power e pi equal to -1, and the equation e to the power e pi plus 1 equal to 0. This equation combines 5 of the most important constants in mathematics. And here I want to show something about the frequently used Taylor series. Here, these 7 series are frequently used in mathematics example and applications, so they are very important. And here is the last slide, and I would like to thank you for your attention for my presentation. And so, thank you.